First things first, what is a neutrino? It's an elementary particle that's incredibly tiny, even by subatomic standards. It's neutral with an extremely low mass, and it's governed by extremely weak physical interactions. All of which means that neutrinos seemingly have very little impact on the world around them, although they remain vital members of the subatomic structure. They represent the building blocks of matter at its most fundamental. They're also traditionally very difficult to detect, even indirectly, because they're so small, light, and physically quiet. Talk of neutrinos first came about in around the 1930s, largely through the work of Austrian physicist Wolfgang Pauli. At about the same time, so many other slightly bigger subatomic particles were also being mapped out. It was Enrico Fermi, though, who reportedly first coined the term neutrino. In those early days, the neutrino was a theoretical concept only, until various experiments started yielding tangible results so as to prove its existence. For example, it wasn't until the 1990s that scientists were able to confirm that neutrinos did have mass. Until then, they were assumed to be massless. So difficult had it been to measure them. Although many years have passed, still with nothing by way of a direct observation of neutrinos then, scientists have long been confident that they are there. And because these particles are so unaffected by the world around them, we know that they can pass through most things. With one of the most often cited neutrino trivia tidbits being that literally trillions of them pass through our bodies every single day. Once we have a higher understanding of neutrinos then, it's thought we might be able to use that knowledge to develop better, longer distance and more reliable methods of communication, for example. But more generally than that, it's hoped that we'll be able to better understand how the universe works at the most fundamental level. In late November 2021, with this goal in mind, a study published by a team working at the Large Hadron Collider at CERN in Europe provided us with the latest update in science's ongoing search for neutrinos. Some reports quickly claimed detection of neutrinos for the first time ever, while others claimed detection of the signs of neutrinos for the first time ever. So what's really going on? The LHC experiment in question actually took place in 2018, and it involved the first run of a prototype of a future accelerator setup called PHASER, or Forward Search Experiment. PHASER is scheduled to start full operations in 2022. And according to the test run's accompanying multi-authored paper published in Physical Review D on November 24, 2021, it's, quote, designed to directly detect collider neutrinos for the first time, end quote. Although, in its title, the paper still refers to these early PHASER findings as, quote, first neutrino interaction candidates only at the LHC. In simple terms, the experiment involved dense layers of lead and tungsten positioned in between layers of emulsion. The particle accelerator was then revved up, the resulting neutrinos were smashed into the lead and tungsten, and in some cases they left behind measurable marks or tracks in the emulsion. And these are the key bits of data. The reality is then that the PHASER prototype still hasn't directly recorded neutrinos in action. These particles are still too small and elusive for that. But what it has done is measure for signs of neutrino interaction with other particles of matter, finding at least 6 examples of it. One of the study's co-authors, the physicist Jonathan Feng, said as part of a press release that, quote, prior to this project, no sign of neutrinos has ever been seen at a particle collider, end quote. It's another important distinction to make, because the latest results at the LHC don't double up as the first neutrinos seen on Earth as a whole. That's because we have other facilities, such as the IceCube Neutrino Observatory, another CERN project, but this time at the South Pole, that have already detected many neutrinos. It's just that most of those examples came from space, from high-energy cosmic events potentially unfolding light years away from us that beamed neutrinos in our direction at close to the speed of light. But now we're capturing these elusive particles within our own machines. They've been generated by us and not by the mighty occurrences of the universe. What's exciting, though, is that the November 2021 paper should also prove to be only the beginning. According to another of the study's co-authors, David Casper, once PHASER is up and running to full capacity, it should register more than 10,000 neutrino interactions, compared to the 6 it clocked this time. What's more, researchers intend on using the same setup to further investigate dark matter, too, now that they know that the general process works. And there are hopes that it might detect other, new, never-before-seen particles as well. As with most experiments at the LHC, the broad goal is clear: to better understand the universe. But scientists are particularly excited about working with neutrinos because they kinda represent the lowest known level of subatomic study, an ultimate in elementary particles. So what can we expect in the future? First of all, the leveling up of phasor and more studies published to analyze the neutrino interaction candidates that it yields when it runs between 2022 and 2024. CERN will also, no doubt, continue its efforts to harvest neutrinos that reach Earth from space. NASA, too, has various facilities designed to pick up signs of neutrinos from the Sun, from other high-energy star events, and from other cosmic structures. Quantum science is so often branded one of the most exciting fields out there because, one, there's still so much for us to learn, and two, we appear to be on the brink of learning a lot of it. Facilities like the Large Hadron Collider will naturally continue to host similarly innovative experiments. But still, what's the end game? For many, it's to reach that holy grail of all of science, a theory of everything. Seeing as, according to our current understanding, you can't get much smaller nor more fundamental than a neutrino, experiments like this latest one at the LHC really are stripping back life, the universe, and everything to its most basic components. And when we get to that stage, perhaps the deepest secrets of why we're here, why anything physically exists, will finally make themselves known. For a long while now, our first inclination whenever existential questions arise has been to look to the skies. That is, to look further out, across the horizon, in the hope that the answers we seek might be somewhere out there. But while we do continue to look out into space, and with good reason, more and more scientists are also imploring us to look within, to forget the biggest things in the universe like stars and planets and galaxies, and to focus instead on the smallest. The physicist John D. Barrow famously proposed that we should aim for micro-dimensional mastery, as a kind of reverse on the Kardashev scale. While the Kardashev way of thinking tells us to search for bigger and bigger signs of potentially greater and greater civilizations, Barrow's microscale tells us to get a better and better grip on subatomic structures. With that in mind, the understanding of neutrinos could become crucial. We're still a long way from that enlightened future time, but we are now, it would seem, generating and to a certain degree controlling neutrinos for ourselves. This latest LHC experiment has lit the way for more just like it, only far bigger and with far wider consequences. We are then coming to terms with life's tiniest parts, and who knows what effective superpowers that could one day grant us. What would you do if you could break down and understand reality at its very, very smallest? Although for now it's just a few small marks in the emulsion sheets of a purpose-built particle accelerator, this is science that could one day change the world.